NYU. She's going to talk about, she did her background in high-energy particle physics, but today she's going to talk us a little about observations of ultra-high-energy cosmic rays.
With luck, I seem to have destroyed this thing already.
That's all right.
Does this do the right thing? Can you guys hear okay? I guess this is not for you, it's for his machine. Anyhow. Well, part of the reason I wanted to start promptly is that I felt like going into some pedagogy on this subject, because it's so different from other parts of astrophysics, the whole process of detecting cosmic rays. And I think that it would be pretty valuable for people to have a kind of general view. At least I find that I can remember things better and think about them better if I actually understand it instead of just some bunch of facts. So anyway, as a result, I'm going to spend the first half of the time at least talking about sort of issues of detection of the cosmic rays and interpreting them. So there's sort of two pieces to the talk, which are, hopefully I won't exhaust you on this phase, and then at the appropriate moment, about halfway through, I'll shift to the results. But anyway, it's irresistible to mention the history because it's so charming. After maybe people know this, so if everybody knows it, stop me. But after the electroscope, after radioactivity was discovered and they developed an electroscope to measure it, they went around measuring everything, of course, and they quickly discovered that there's a residual radiation. Even when they go far away from their sources, there would be some sort of counts, which they assumed was attributable to the Earth. And of course, that's an obvious thing. And it was ultimately correct. But Hess was apparently a very, very bold character, and he might have also liked ballooning, I suspect. Anyway, he decided to go up in this balloon in 1912 and take up an electroscope, and he flew to 4,880 meters. This just seems incredible to me that somebody would have the nerve to do that. Anyhow, he was happy as he went up. The first 1,000 meters, the rate declined exponentially, as you would expect. But he didn't stop his experiment soon enough. He must have been enjoying the view. But he kept going up, and then the rate increased. And this remained a mystery for literally decades, what that could be. This was more pictures of his exploits. You can see that it was quite a public interest.
If you write at Vienna?
Excuse me?
He started right at Vienna?
It's outside. It's right in that neighborhood. Anyway, I'm sure most of you have seen this, but it's going to be pretty useful. And it also does emphasize just the tremendous range. There's something like 32 decades of flux and some 12 decades of energy that these are observed over. The galactic cosmic rays start to end in here. Galactic acceleration of protons ends about there at 10 to the 15th electron volts. We'll be really interested in the extragalactic stuff. This is called the ankle. One reason I wanted to show this plot is to emphasize that the flux is really falling very rapidly. In the other plots, I'll often multiply it by e cubed, so you can see better what's going on, but you lose sight of this very rapid decrease. Well, I also can't resist. You guys know about acceleration sites. But anyway, to keep in your mind, the low energy stuff is mostly from the sun. Medium energy is galactic, and because of the limited magnetic fields of the galaxy, they leak out. And then the interesting question we'll be addressing are the ultra-high energy ones. Anyway, but I can't resist the trivia either. But it's also an opportunity to tell you this unit. So the unit of energy is the ecto-electron volt, or EeV, and it's 10 to the 18th electron volt. So the energies are tremendous. This is always impresses people. But this is actually perhaps practically important. The relativistic time dilation factor is so big that a neutron, instead of being a 10-minute lifetime, has a lifetime of megayears. And that might actually mean that we can see in not too far away sources, neutrons, of course, are not deflected by the fields, which normally bedevil the lower energy cosmic ray studies, but we may actually be able to see sources in neutrons. Of course, the magnetic field bending decreases because these are relativistic particles, like 1 over their energy. So hopefully at high enough energies, one can see them directly pointing toward their sources approximately. But this is another number that's worth remembering. It's easy to remember. The rate of the flux is 1 per square kilometer per century. So for these high energy events. So I'm going to mostly talk about results from the Pierre Auger Observatory in South America. And there's two, in Argentina, there's 2 pieces to it. And this has been a breakthrough in the field, that it's got 2 parts. It's got a surface array of detectors. I'll go into the specifics of the detectors more later. But this shows the array. There's 1,600 water tanks on each of these little blue spots, spread out over 3,000 square kilometers. So at the rate of 1 per square kilometer per century, you get about 30 events a year at the very highest energy. But in addition, there are 4 air fluorescence telescopes. So what happens when the cosmic ray hits the atmosphere? This is the first part of the whole story about why the process of what you can learn is rather different than what you're used to. So what happens is the high energy particle, which let's say is a proton or a nucleus, it'll interact with some nucleus in the air, and then it will produce some number of secondaries. But that interaction is vastly higher energy than the LHC. The secondaries on average, so it will typically produce 1,000 secondaries. But each of those secondaries still has vastly more energy than the LHC. And so those will also produce thousands of secondaries until you build up this very high multiplicity shower. Something that this figure doesn't show, but I need to emphasize, is that you can think of the shower as having 2 components. Because in any given interaction, most of the particles are really high energy. And those, just like in gamma ray bursts, they get collimated forward by the relativistic beaming. But some of the particles are low energy. And so those come out at relatively wide angles. And so what happens is the showers, most of the energy of the shower is in this very, very, very intense core. But there's kind of a halo that surrounds it that constantly dissipates but gets renewed. So as the high energy events, shower particles are plowing through the atmosphere, at every given stage, low energy ones are emitted and produce this kind of a halo. High energy ones re-interact. Those interactions include low energy ones, which repopulate this halo. And so what happens is that you have this very intense central portion, and as that, it's just like a very intense electric current, mostly electrons and positrons. And so they excite the air molecules that they're passing to fluoresce. And that air fluorescence, just like in a neon light, you can see with a telescope. And so there's 4 telescopes that look over this field. They look at relatively low angles. And so they don't see the very beginning of the shower. And if the shower was pointing right at them, they wouldn't get a very good view of it, and so on. But if there's a large region, well, if so, a low energy shower might hit and just be seen by 1 telescope, and its halo will get detected by the water tanks. That's the basic idea of the experiment. And now that the array has been complete, or essentially complete, for several years, these little holes are where savvy landlords decided that they would try to ask for more rent after the fact. So this is a picture of a typical water tank. They're just cheap plastic. They've got a solar panel. They've got a radio transmitter to transmit the data they collect. They have inside them, so this is filled with water. And inside, so there's 3 large photomultipliers which just look at the water. And when charged particles hit this tank, they produce light in the water. If they're electrons and positrons, they just create a small pulse. If they're muons, they create a kind of characteristic signal. I'll show you. But really, you just get the integrated light that comes out. This is one of the 4 telescopes that, as I said, was looking out over the array. These are just garage doors that get opened at night. So looking at the core with these fluorescence telescopes, of course, you can only do on a dark, pretty cloudless night. So about 10% of the events get seen in what's called a hybrid way, where you see both the air fluorescence and you see it in the water tanks.
Why do you need cloudless months?
I'm sorry?
Why do you need cloudless months?
Low.
Cloudless.
Oh, I'll show you that in a minute. Right. Okay, let me continue. So this is an example of, since you guys are astronomers, you might be a connoisseur of the telescopes. But basically, there's just a large bank of photomultipliers that the light comes in and gets reflected onto this detector. It's pretty hard to sort of make sense of what's happening in any of these pictures. And then what happens as the shower passes, in real time, it passes on here. And you monitor not only the amount of light, but what time it arrived. And this is, I still haven't gotten quite to the signal. But this is an example to help you visualize of what a very high energy event that happens to fall in the middle would be seen by all four, and this is a real event, was seen by all four telescopes, and these are the tanks that it triggered. You can see at that time the array wasn't complete, and there were big areas, so we were sort of lucky that particular event was found, but now there's a bunch of them. Let's see, I guess I thought I had a picture of the, well, maybe it'll come later. Maybe I took it out to save time. Oh, well, I did take it out to save time. I'm sorry. I had a picture showing what the signal looks like on this bank of photomultipliers, and basically you see the light come in a sort of in an arc, and by the timing you can get information on the trajectory of the particle and the plane of the arrival. So this would be a typical readout. This is the tanks on the ground and which one's fired. By the timing of the tanks, you can work out, you can imagine if your shower's coming like this, that would be sort of a wave of arrival times. And so with that method, just the tanks alone give you about a 1 degree resolution. If you have both tanks and the air fluorescence, you typically get a half a degree or maybe better. So this is a plot as a function of the column depth. It's usually called capital X. So along the way the shower develops is to a very large extent just governed by the number of interactions that have happened. And so really the main thing that matters is how much material did it pass. And so you can plot any shower independent of its. So of course if it comes straight down, it gets to you after a much smaller amount of material than if it came from the side. But so they're typically shown as a function of the column depth. So this would be the data from the air fluorescence, from each of the different air fluorescence phototubes. And they're looking, you can infer, you later fit to the direction and so on, and you can map the position in the phototube to an arrival depth, an atmospheric depth. So this is the amount of signal seen as a function of atmospheric depth. And essentially, it's plotting out the number of charged particles in the shower as a function of atmospheric depth, because basically the amount of air fluorescence that's produced is proportional to the number of charges. The reason you don't want clouds is that if you have clouds, they will obscure part of this path, and then you can't interpret it very well. So there's lots of effort to monitor clouds and eliminate cases where you have clouds. One of the things that for which one could use this for is to study particle physics at ultra-high energies. And there's a certain kind of exotic phenomena that can happen in particle physics that would produce strange distortions of this shape. And so you have to do that very, very well, too. You have to do cloud monitoring and stuff like that very well to be able to interpret this. The way the shower develops as a function of depth is a key indicator of what initiated the shower. I'll try to show you that in a minute. But let me now just give you an update on what the detector is like. So this was the exposure as it was. This is the sort of the integrated observation capability, let's say, as a function of time. That's more or less when it was completed in terms of its dimension, and so it's more or less linear after that. And this is where it was last summer, and now it's something like up here.
Could you come back to the last figure, please?
Sure. So this is one particular event which was detected both with ground detector and the fluorescence telescope.
And so this was initiated. So I'm trying to recall my atmospheric ancient history knowledge. So the Pfotzer maximum, isn't it at about 100, which is why you fly?
The what is a maximum?
There's a maximum at about, I thought it was 100 grams per centimeter squared, but maybe I'm wrong.
A maximum of something else. This is just...
No, but that is where the shower develops, and it's why people can't fly too high, because there's too much cosmic ray stuff that's raining down.
Oh, okay. All right.
But maybe for the really high energy events, what happens is that it's shifted down.
Absolutely.
Time to develop. Is that?
What happens is that the process of, in order to develop a large number of particles, you have to share out the energy.
Yeah, so it's a big
and so it just keeps going and going and going. Whereas the low energy ones all happen just down
right,
here.
Good. And so the peak moves closer and closer to the ground.
That's right. And we're going to see
more and more energetic.
Absolutely. And we're going to see later that this is the place of the peak is called Xmax. And the value of Xmax on average is supposed to increase with energy. Yeah. And moreover, very importantly, the behavior will be a diagnostic of the composition. And I'll try to convince you that it would be really great to know the composition, and that it's pretty tough for various reasons. But in principle, that information is somehow embedded in that in the Xmax.
The composition
what was the right? Is it a proton? Is it iron? Is it a photon?
But once it develops, it probably forgets.
It's the initial part of the shower, however, so I'll get to that in a second. Good question. All right, so anyway, the number of square kilometers available now is huge, and so the number of particles detected is very big. There's something like almost now 2 million events that have been reconstructed, well over 5,000 events above 10 EeV. And that starts to be the really interesting region. Okay, so this is the one picture. I returned to this just to keep your mind focused. But anyway, you have some first interaction. Where the first interaction takes place, how deep in the shower, depends on what the total cross-section is and if it's a proton or an iron, because the cross-section for iron is much bigger than the cross-section for proton. So the first difference, just taking proton and iron as extreme cases, is that iron will interact much quicker, and because it's got a lot of particles, it would immediately give a lot of energy into multiplicity. And so in that case, the shower grows much more quickly. And it's also much more consistent about when it starts, because you're averaging over 56 different showers. So in particle physics, a very high energy interaction has a lot of personality. It might be diffractive, something like 10% of the time. Only a few particles are produced. It's like one set of quarks tickles the other at sort of a long distance, and only a few particles are produced. But other times where they collide more head-on, there are thousands that are produced. So in a PP collision, there's a huge variation from shower to shower. So what that tells you is that if it's a proton-initiated shower, the development of the shower will vary a lot more from one interaction to the next. And so going back to this plot, if we had a whole lot of events and we looked at them, and and by the way, in this case, the integrated area is a pretty good measure of the total energy. And then you make corrections for neutrino energy losses and stuff like that. But that's under pretty good control. So anyway, but the position of this will shift around. If you see a lot of shifting around, that's a hint that it's protons. If you don't see much shifting around at all, that's a hint that it's a heavy composition. Okay. One of the things that's problematic, so I was making this remark, that there's a big range if it's a PP collision, a p-air collision, in the number of secondaries, but that information contains information on the composition. But the other thing to say is there's a huge extrapolation in energy in the knowledge of the particle physics. I'll come back and show you a plot that makes that clear. So even though we think we know particle physics up to the, I didn't say even that. Even up to energies where we already have accelerators, there's an awfully lot we don't know about the interactions, because if the protons collide but you get particles that are almost along the beam axis, it's extremely hard to detect those. So there are aspects of the particle physics, even at LHC energies and below, that are really uncertain very now. And furthermore, the nuclear physics may be very much more complicated than we understand. So what people do when they model these showers is they rely on what are called event generators. So these are programs that on a Monte Carlo basis generate events. And they're used for, they're very, very important for particle physics experiments, because people use them to understand the detector, and they use them to model the observations, and they tune these event generators to agree with what's seen. But of course, since you're not looking at every aspect of the event, you don't get it right. And they're not based, they're sort of inspired by fundamental physics, but they're absolutely not constrained by fundamental physics. I wanted to emphasize that because in a minute you'll see how some of the conclusions are ambiguous because we don't know the particle physics that well. Of course, the flip side is that if you can use astrophysics to constrain some of the, like what the particle content is, then you can learn some very fundamental particle physics.
Follow on this TeV, center of mass. Can one think of it being a point interaction of a gluon or whatever it is with a particle? Like, does the rest of nucleus really matter at these energy scales?
It's because for a given gluon quark interaction, it's trivial. But there's a huge density of gluons. And so there's a huge number of interactions happening all on top of each other. And a lot of them are at low momentum transfer. And so a lot of them you can't do QCD. So the particle physics is very, very non-trivial.
Even for the very first.
Excuse me?
Even for the very first 100.
Yes, that's right. Because if you think of it, the right way to think about it is, this is not intuitive probably for you, but as the energy of the particles increases, the effective density of the virtual constituents increases. And so you get to the point where there's so many gluons and quarks and antiquarks that people use terms like color glass condensate. They try to use very, very different approaches because it's absolutely not a point-like particle physics problem. So even though if you did happen to have at the LHC an interaction where you produce very, very high momentum secondaries, that you could successfully model, because you can infer after the fact that if you got really high energy collisions, you had an initial high energy process. But for almost all of the rest, it's some very complicated thing. And we're summing up over everything, and those high energy ones are really rare. Those high momentum transfer ones are really rare. Okay, now as model independent facts, what we can say is, though I mentioned all of these things before, the energy in the core is by far dominant, so we can, using the FD detector, fluorescence detector, you can measure the energy well. Using this halo, you can try to infer other properties of the events. And if it's a heavy nucleus, it's pretty much, it's characteristically a little bit different. But I'll show you in a while that protons could even fake a heavy nucleus if the cross-section increases faster than we think. This is just another fact that you guys might want to have in mind. This is as a function of the depth in the atmosphere of some typical shower. This is the number of electromagnetic particles, so E plus, E minus, and photons, as a function of depth. And this is the number of muons in the shower. You have very few muons at the beginning, because to get muons, you have to have a charged pion decay. But because of their time dilation, they have to lose. It's only the low energy pions that can decay before they interact. But as you go deeper in the shower, you produce more and more of these low energy particles, and so eventually you have produced a lot of all your muons. So anyway, the number of electromagnetic particles is much higher, because at every stage in the interaction you produce pi zeros that feed the electromagnetic cascade.
What's the ratio of pairs to pions?
Pairs to?
Pions in the heat?
You mean in this region?
Yeah.
Well, to decayed pions, it's a factor like that.
Sure.
To
But
charge.
I mean, most of the particles are still strongly directed in the shower.
The electromagnetic part of the shower generally dominates the hadronic part in numbers, but the hadronic part dominates in energy. So this shows the distribution. This is the distribution of Xmax as a function of, this is a histogram of the values of Xmax that you would have for a 10 to the 19.5 eV proton shower. And one of the things I wanted to show you, the point of this plot was to show you this is where ground level is for a vertical shower, this is where it is for a 30-degree shower, and this is where it is for 45-degree shower. So depending on where it comes, you see the shower at a different stage in its development, which is good because it means you can test the particle physics, since what's coming at the Earth is independent of zenith angle. Okay, so the first goal is to measure the spectrum well. And I'm not going to go through all of this, there's just because of the time. But the strategy that was developed, which I think is a very good one, is to use the fluorescence detector, which is monitoring a large amount of energy, to calibrate the energy of a shower, and then look to see what an event, that same event, looks like in the ground array. Because the ground array gets 10 times as many events, and it's much easier to calculate the aperture. So by doing that, you get a much more reliable determination of the spectrum. Yes?
So first, there's more information in the shower. So there's also radio emission generated in the shower.
And in fact, people have set up radio detectors now. And
are you doing this as well? Or?
Yeah, at NOJ, but we don't yet have results to report.
Okay. And
Absolutely.
here's sort of gamma ray emission generated by, I think, pi zeros that could actually sort of figure some direct radiation could also be sort of looked at. By
And the shrink-off, so I simplified, this core of the stuff emits fluorescence radiation and also shrink-off. The shrink-off tends to go forward, and so it sort of hits the ground, and it's collimated. So, but it's a sort of annoying background, but it definitely does have to get modeled. So this is an example of plotting the signal in the electromagnetic, in the ground array versus the signal in the energy measurement in the fluorescence detector, and using this relationship, the so-called hybrid events, you can calibrate your ground array very well. Interestingly, there looked like there was a sort of 20% or 25% discrepancy in the energies, which only within the last week or so has been resolved because an independent experiment did a better job of measuring. The key thing is how much does the air fluoresce when a current goes through it. And this has been measured periodically over 40 years. It's a very hard experiment. Turns out that those old experiments that had been relied on were sort of 20% too low. So now the discrepancy within OJ seems to be all cleared up, because now that this other independent number is better known. It was always in our systematic uncertainties, but it's quite nice to know that's true. In any event, here's the spectrum, but multiplied by e to the 2.6 to flatten it out. And this is now in units of the log of the energy. And you see that it starts to steepen. And so this is likely to be due to the fact that you've got energy loss for ultra-high energy particles, which I'll come back to. So that's a hint that and now the statistics are just enormously better than they ever were. So there's no discrepancy now, as you've probably all heard, with this GZK prediction. I haven't told you what that is yet, but for the moment I'm assuming you know, but if you don't, I'll explain that in a second. One of the things that's very interesting is you could have a drop-off in the spectrum without having seen this GZK effect, which shows that energy, above a certain energy, you lose a lot of energy during propagation off the CMB, scattering off the CMB. Because after all, it might just be that the accelerator, whatever it is, can't accelerate any higher than that. So that has to be disentangled, and we know how to do that, and I'll explain that to you. Okay, so I tried to hurry through that. That was more or less halfway, giving you the background. But I hope that'll help you understand then what are the things, what are the limitations on what physics we can get. It's kind of a bootstrap process. As things get understood, they all fit together, and you understand something else then, and so on, and we can make progress. So the questions we want to understand, and I'll talk about the rest of the time, is what is the evidence about what the cosmic rays are, what their composition is. The interesting thing is that there's sort of conflicting evidence on this. And of course, we really want to know what the sources are. It would be great to know whether they're bursting or continuous. And interestingly, as I'll try to explain, I hope I didn't delete the slide, we can tell that by the spectra of individual sources. Of course, trying to correlate with astrophysical catalogs is, in principle, a way to do this. But one of the complexities is because of magnetic deflections, what the correlation is going, what the correlation should be is obscure. You have to just sort of do everything at once. And I'll argue that, again, there's some things we can't say yet definitively because we don't know the particle physics well enough. And then eventually we'll be able to use these to constrain extragalactic and galactic magnetic fields. Okay. I guess I could ask if there are any questions about the detection side of things. I'll carry on. Okay. So first let me say why the composition matters. Well, one reason is that if you wanted to do particle physics with this, you have to know what your beam is, whether you're doing heavy if you're doing quark-gluon plasma kinds of physics with nuclei collisions, or whether you're doing a proton on one of the protons in an air nucleus. If it's a PP collision, one of the protons in the air nucleus and the incident proton, the energies are up to 660 times higher than the center of mass energy in the LHC. So from a particle physics perspective, it's absolutely fantastic. It gets you well into the regime where exotic things ought to be happening, whereas the LHC is kind of at the borderline. If it's the energy of the so-called GZK energy, beyond which there's far fewer particles, corresponds in the center of mass to 350 TeV. So this is 20 times the LHC. So there's lots of events above that energy. And so really the prospects for particle physics are fantastic. And if it's actually iron, then the energies of the quark-gluon experiments would be amazing. Of course, for astrophysics, it's really important to understand what it is. I mean, if it's a heavy iron, and you were to discover that it was likely to have been made by GRBs, that would really tell you something important about the mechanisms in a GRB. And as I said, the galactic and cosmic magnetic fields are all entangled in this. So this is the spectrum now multiplied by E cubed as a function of energy. And this is lower energies by and large. This is sort of focusing on the galactic region. But just to explain to you what we do know about composition right now. So up to about here, you can do, for energies lower than this, the fluxes are big enough that you can do experiments with in satellites. And you can actually have a detector that actually measures what the particles are. So down here you can actually directly measure the composition. As you get to higher and higher energies and the fluxes get smaller and smaller, you have to do ground-based experiments. And the main experiments in this region are done in Karlsruhe with a detector called Cascade Grande, and that's a thing about the size of a football field, very, very well instrumented. So it measures a lot of information about the showers, but it's limited by in energy because you just don't have enough flux for high energies. So based on modeling, they've concluded that this is the actual underlying spectrum of protons, again multiplied by E cubed. That helium spectrum looks like this. This is a combination of their data, direct measurements down here, and modeling. And the assumption that an accelerator that can accelerate protons to here could accelerate iron to 26 times higher energy, and all that is available as a free parameter is the total number of irons. And so in this kind of a model and fitting their data, they arrive at this prediction. And this is then the 25 to 27, Z of 25 to 27 curve. The reason these are sticking up higher, you might say, gee, how can it be that that's bigger than the proton? Well, remember, it's then multiplied by E cubed. So this just means that probably E cubed is stronger. It's falling not quite that fast. Anyway, if you do this and you add on another piece, taking you up to Z of 92, this is your predicted galactic contribution. And in that model, you have to explain the extragalactic as being this. Now, why would you maybe not like that very much? Well, there's a number of reasons, depending on your perspective, which I'll get back to. But this is the so-called ankle. If we went back to the, well, I won't go back, but if we had gone back to the, if this were plotted in a way that another more modern plot that had, I'll show you in a second a much better plot. But let me put that on hold for a second. I'll show you the other plot. Where is it? Here. So this is a spectrum again from Auger, 10 to the.
Can we just go back?
Yeah. Okay. Hang on, just one second. We'll go back, but let me comment now that you can see how. This is so you can see how what an incredible improvement in the data. So there's how the data goes. This is 10 to the 11 GeV, then it's 10 to the 10 GeV, and that's 10 to the 9 GeV. And now we'll go back.
The only reason is obviously this is one busy figure, and there are things that it looks like everything's been given a uniform prior on this, and of course the biggest error bars are the ones that the others.
Yeah, exactly, exactly.
So it's got, you know, there's no weighted grand average curve, but maybe the reason for that is because one experiment, namely, was completely kills all of these others in terms of significance.
Auger takes over about here and to the right. So this was all crucial to try to understand the composition at lower energies.
And which is considered to be the very best experiment in that other range?
This one that's called Cascade, these various ones. And the other ones, as you say, are very hard to make out, but this was the slide that I could get. But it's useful because it does remind you.
Where is Agasa?
Oh, it's up in here. So all of the ultra-high energy experiments are from here and up. This is 10 to the 19 electron volts. This is, here, I know how I can orient you. The GZK cutoff starts about here. So a big question that's going to be very crucial for the astrophysics interpretation of the ultra-high energy cosmic rays is what's going on and what's producing the ankle. The most simple mind, so what's the ankle? It's because the cross-section is falling really fast, and then it sort of breaks and doesn't fall so fast, and then eventually it falls really fast at the GZK. I keep talking about it without defining it. I apologize. But this is the ankle. Oh, excuse me. Well, I can move this more easily than I can remake my figure. Is it okay now? Anyhow, so this ankle, the natural way to explain when you have you have a break in the spectrum, is to say, well, fine, this is where the extragalactic stuff is coming in. It's got a flatter spectrum, a harder spectrum, and so at some point it will cross over. And you don't have any embarrassment. If this is still galactic, so in this other type of a model, now we can kill the lights. The reason this is so non-trivial, supposing this is where the extragalactic takes over, as you have to do if you believe this fit in all of this composition stuff to the galactic cosmic rays, to fit the total cross-section, you have to, the total spectrum, you have to say extragalactic takes over in here, well below the ankle. What that means is that the level of the galactic and the extragalactic has to sort of match perfectly and just fit right in there. So to my mind, this is a very deep question, so I wanted to call it to your attention to think about. If there was some mechanism to think of that would smoothly extend the galactic component so it goes out into here, and then the new stuff is the extragalactic stuff, in a way that would be much more satisfactory. But okay, I just wanted to leave you with that background thing. That's right. No, people have been trying for a long time. It's not like I'm the first person who thought of this. All right, now on to the extragalactic stuff. So you all know, and finally, what is a GZK effect? It's this fact that on the microwave background and other relic, the infrared background and so on, you can create pions. This is a very, normally when a proton hits a photon, it just doesn't do much. It doesn't lose any energy. But if it actually produces a pion, then it really loses a fraction, 10% of its energy. And so as a result, if you plotted the attenuation length, the energy attenuation length as a function of energy, there's a dramatic reduction when you hit this photopion reaction at around 100 EeV. And as a result, the highest energy cosmic rays are produced nearby. Now, the thing I'm going to tell you now, so everybody, I think, knows this, the thing that's new that you probably don't know is that the story for iron is amazingly similar. The process is totally different. For iron, I didn't draw the plot, but what happens is it's photodisintegration, for any nucleus. A photon comes along and picks off the nucleon, sort of one at a time, or maybe one alpha particle at a time. And so the iron becomes calcium, becomes and so on like that. It turns out that light nuclei and intermediate nuclei are very fragile, but iron turns out to be really robust. And it turns out, this is the plot that's so interesting, is if you look at 100 megaparsec, if you say, I see a 60 EeV cosmic ray, that's kind of right at the place the GZK cutoff starts. I see this cosmic ray. How far away was its source? Well, if it were carbon or helium, the source has to, the fraction of the cosmic rays that could have come from such a distance is 5%. Whereas if it was iron or protons, the characteristic distance is much, much higher. In other words, if I see this event at that energy, and it's a proton or iron, it has a 20% chance of having come from 100 megaparsecs or more. And what's striking in the curve is that protons and iron are very similar. As a result, it's very hard to tell from the spectrum alone what the composition is. So here's the data again. And now I'm showing you some models where these are models where they're protons. This is a model where it's iron. These refer to the spectrum at the source where it's produced. This has to do with the evolution of the sources. But anyway, here's a few reasonable models, and you get more or less an equally good fit for protons and iron.
Just recall a paper by Cooper and collaborators from a few years ago, which got a slightly different, it was on a slightly lower iron cutoff.
You can
Details of the treating of the dipole resonance and so on, I assume.
No, there's very little uncertainty in that modeling because it's low energy collisions. So sometimes people have done better and worse modeling in detail, but fundamentally that's trivial work. And what is changing when people come to different conclusions is what they assume, like what's the composition at the source and stuff like that. So different people have come to radically different conclusions. What I wanted to show here is you could make assumptions with either perspective, which can give you a pretty good fit to the data. Now the data is getting good enough that you might say this really favors iron instead of protons. But it turns out there are other models where you can get a more proton-like shape. One of the things I wanted to point out, though, that's very interesting with protons, if you've got protons at the source, then they naturally, you get low energy ones. But if it's an iron-dominated model, the reason you can get iron winning is because you say the protons can't be accelerated to that high in energy. And therefore, in these models, you really have to have a galactic explanation below about 10 to the 18.5. So it's interesting to me how the whole issue of what's going on with the galaxy really feeds directly into what we infer about ultra-high energy cosmic ray composition. But my main message here is that at the moment, we can't unambiguously say on the basis of a spectrum what the composition is. It could be proton or iron. They both have a similar cutoff. I don't think many people are kind of aware of it, so that was an important part of the message. And but that it can be an important element along with other evidence to try to decipher this composition story.
What is M?
M is if you say the sources evolve according to 1 plus z to the m. I mean, that's a very unrealistic thing. Actually, Svi and I are working with some of these people that do these models to give them some more astrophysically plausible choices of the evolution. All right, so the other indicators of composition are quite confusing. I'm going to show you in a minute that if you just literally look at the Xmax distribution with naive models, you would conclude it's most likely heavy. But if that's true, if it's iron, then the deflections in the galaxies are radiant, huge deflections in the galaxy. And so then you would expect no correlations whatever. So, of course, I've just argued that, well, and I'll argue some more, that the particle physics is not well enough known that we should necessarily believe that. Correlations with extragalactic astrophysical objects, like galaxies, suggests that they're a low z, so that they don't get deflected very much by the galaxy. But then maybe the correlations are accidents. Okay, let me run through this. So very quickly, there's something called the elongation rate, which is precisely, I think you have a future in this field if you want. The Xmax is a function of energy. And so as we were saying, that the predictions are that the depth of the maximum, Xmax, increases with energy. And it's generally deeper if it's protons than if it's iron. If it's iron, it develops quicker, so the X is lower. So these are different models, and you get an idea of the model dependence. Well, this is the data. There's now another point, which is sort of over here. So you could say that the data really looks like it's favoring a shift from a light composition to a heavier composition. This is another measure which has to do with the variance in the X's, which I had always thought was a very robust measure, that you would have a lot more variance with protons than with iron. And these were the proton models, and these were the iron models, and this is what the data does. Interestingly, this is now the proton-proton cross-section. Or maybe this is proton-air cross-section, I guess. Sorry. This is the data from accelerators and making a naive model of how the nucleus works. And these are different extrapolations. And it turns out that if you, and this is where the LHC is, it'll be very useful. Anyway, if you were to extrapolate sort of like this, a little bit higher than that, which is not necessarily excluded by any means of the particle physics, then the behavior of the Xmax and so on of protons is essentially the same as used to be predicted for iron. So really, if that were correct, if these extrapolations were a little bit bigger, if it grew a little faster, then the Xmax information would not be inconsistent with iron. So one possible resolution of all of the contradictions is that the proton-proton cross-section grows a lot faster. It's really light nuclei. And then we can understand the correlations. And then people who want it to be GRBs are happy and so on. Okay, well, I have to keep pushing along. Clearly, the correlations depend on how much they're deflected. The Larmor radius is about 100 kiloparsecs if you had a microgauss field and a charged 1 particle and it had 100 eV. Oh, well, this is some estimated deflection. Maybe I won't go into that. Some work that a former student, now postdoc, and I have done on the magnetic field, constraining it with WMAP and rotation measures, and we've gotten a vastly better, more consistent and systematic fit. We're just putting out a paper with Brian Gensler and Elena Fayen using a lot of new rotation measures. So anyway, now the galactic magnetic field is much better understood, including the random part, and it's fair to say that now we can use that. That's going to help a lot. Let me quickly move through some evidence for correlations. There's a very under-discussed set of a cluster of cosmic rays. The reason it's under-discussed is that it appears, in order for it to look significant, you have to combine the data of two different detectors. Of course, that's reasonable. There's nothing wrong with that, except that two different groups hated each other. Maybe I should, that's too strong. They were in strong competition. They didn't want to cooperate, but the data was out there, and with their approval, I did the study. And what you find is that, so this is a picture of it. It happens to be in the direction that Sloan has looked, and so the foreground is very well known. The little black dots are Sloan galaxies. The gray circles are the cosmic rays. There are 5 of them. The size of the circle is the accuracy to which the cosmic ray arrival direction is known. That's sort of 1 degree. And they're perfectly consistent with almost no deflections at all. Or they could be deflected together with about that amount, which is consistent with what we know of galactic deflections. And if you look in the foreground, this is a cluster, this blue thing is a cluster of a pair of clusters of galaxies that are colliding. So that sort of was exciting, but maybe it's just a coincidence. But that's where they are here, and you see the foreground is really empty. So this would make a coherent picture. You would say, well, the reason they're so little deflected is that there was just this huge void, and so there's exceptionally low magnetic field in that direction. And if you did that, you would know also there would be a smoking gun that the source was at that distance, and that makes a lot of sense. So if you do that, what you can do the following. You can say, I forgot to say this. You can say, one of the things that's very exciting is if you can find and identify a cluster from a given source, you can really directly say, is that a continuous source or is it a bursting source? Because if it burst, then all of the cosmic rays that come to you started, it's a race. The highest energy ones get to have the shortest track because they don't get deflected very much, so they get there quicker. The lower energy ones take longer. The lowest energy ones take a really long time because they have to go a longer distance because they get deflected more. But that means that as you look at the spectrum changes with time. And so immediately after the burst, you would get a high energy spectrum. As the time goes along, you shift the peak of the spectrum to lower and lower energies. Meanwhile, the size of the spot increases. So you can do that with this cluster of 5 events, and it fits very well a bursting source, and it doesn't fit a continuous source. So that's I thought that was very intriguing. But the energy, total energy, looks like it's a lot lower than what a GRB would produce, which is why I got interested in trying to think of non-GRB bursting sources. Well, this is another topic. Okay. So the famous correlation from Auger was correlating cosmic rays, these are the cosmic ray events, with Varone objects that are likely have a higher than average chance of being an AGN or, well, it's a combination, mostly AGNs. And so this came out a few years ago. But this has been very puzzling, and you may have heard some more about it, because this is the number correlating as a function of time, and this is so there was a period when the correlation was, the prescription was made. Okay, if they come within 3 degrees of one of these Varone AGNs, we'll call that a correlation. So then after that, you trace the number. Well, the correlation stayed very high, much higher than you would get by chance. But then after the data was published, the subsequent events just didn't correlate for quite a long time. And then after that, they just kind of stabilized. These bands, this is the probability of correlation, and these bands are the 99% chance. So this is no correlation, and if the gray line included that, that means there's more than a 1. Try to say this. Since this is since the gray and blue area in the data are not touching that line, it means the chance is less than 1% that you would get as strong a correlation by chance. So anyway, there still seems to be a significant correlation. However, that's not a very great way to my mind, to do this thing. It's for a variety of reasons I could discuss with you. So I'll tell you about something that will be closer to your hearts and is new and interesting. So what we've done is we've cross-correlated the cosmic rays with a nearby matter distribution. And this just projects the 2-mass galaxies out to, in this case, 70 megaparsecs and out to 120 megaparsecs. And this is the 2-mass autocorrelation out to those, for those 2 data sets. And then we can say, well, what happens if we cross-correlate cosmic ray arrival directions? Given their energies, you would guess that about 70 megaparsecs would be the most sensitive depth to use. And this is then the distribution of 2-mass galaxies out to 70 megaparsecs, and the red things are the Auger cosmic rays. And this is the cross-correlation. The red is the cross-correlation between a cosmic ray and a 2-mass galaxy, and the black is the autocorrelation of the 2-mass galaxies, just the same plot as on the other slide. And the dotted lines are what you would get just by taking random data sets and asking what you get for the cross-correlation. So this is some measure of the sigma, if you like. And so you can turn this into a significance that this red line, the cross-correlation, isn't actually 0, showing no correlation. And what you find is that when your sample depth, I said that you expect the sample depth to be most sensitive at around 70 megaparsecs, and indeed between about 60 and 90 or so, it's pretty, it doesn't matter. It also depends a little, but very, very little, on where you cut off your fitting, you're trying to fit it to 0. But anyway, it's quite insensitive to that. And you find that the significance of such a strong correlation is just a few tenths of a percent that you would get that by chance. So what do I conclude about that? Well, this is just different ways you can look at it. So depending, this is just, I won't take the time to explain, but this is just slicing and dicing it a bunch of different ways to show that it's really that conclusions are very insensitive to how you do it. But the upshot is that if you put this energy threshold at around the GZK threshold, then the chance that you would get such a strong correlation with nearby galaxies by chance is very, very small. It's a few tenths of a percent. which I take as being real evidence that there aren't huge deflections. So to my mind, what we know right now is that most of the cosmic rays are protons, because we know that the helium or carbon, that intermediate light stuff, has a very unlikely to get to us from anywhere that's not really close. So I sort of exclude that theoretically. And so I think that the most consistent interpretation right now is that they're protons, there is a GZK effect, and that we're seeing the effects of new particle physics, not new particle, it's not discovery of black holes or something like that, but it's, we're the reason for these indications and the shower development looking anomalous to us is that we just haven't understood the high energy peak cross-section very well. By the way, the theories are all over the map for that. I might end showing you a thing we're doing in New York, maybe, which is to make a neutrino telescope using water tanks. This is actually some volunteers at NYU. The idea is that if a neutrino is coming in, it just can skim the Earth, convert in the Earth into a tau. The tau decays over your detector and makes a very big event. And Auger has looked for these but hasn't seen them. But if we use water tanks on New York, they are on every building over 6 stories. This is a partial map of them. Then you can have a very dense array very cheaply. And so we did some simulations. This is, and by the way, it's better by a factor of 10 than IceCube. For this particular signature, it's pretty comparable to IceCube and the other channels. Anyhow, so we convinced ourselves that we could see of order a few events a year. We probably want to do more than that, so we'd have to make it bigger. So I figured I would amuse you by showing you some pictures at the end of these water tanks. Now, next time you go to New York, you'll start looking at water tanks. Okay, this is the Auger PR. There's a proposal that you may know of to make a much, much, much larger array, at least 7 times larger in Colorado, with an even bigger spacing, so it's not too expensive. And it would just be, they would both do different kinds of physics. So maybe given the time, I should wind up. And I think I'd like to say that the original puzzle in the field about the GZK shape in the spectrum, that's not a puzzle anymore. I didn't mention to you, but we can definitely exclude that the cosmic rays are some exotic thing. All these exotic physics models that have been proposed, that they're cosmic necklaces and stuff like that, is just excluded because those predict that they're photons, and that's now definitively excluded. And then I wanted to argue that I think they're most likely to be protons. And well, there will be more information forthcoming. Thank you. See if you can, the first person who deciphers this can.
Exactly as the EP cross-section at high energies, the uncertainty folds back into the depth shower maximum?
Because if it's a bigger cross-section, then the proton, two things happen. It interacts quicker, and therefore the Xmax is a lower value. Once the first interaction happens sooner, then the rest of the interaction builds up faster. But the other thing is that if it interacts sooner, if the cross-section is bigger, then there's not as much variance in the depth that it can happen at.
That's would be my second question.
Yeah, so it helps you in 2 ways. Yes?
This may be a horribly named question, but what about things that are heavier than iron, that have decay radioactivity?
In the galaxy, that's thought to be relevant. It would be very nice to understand what the abundance should be. But for extragalactic ones, I think it's already, the abundance is already so tiny of iron that, I mean, in principle, if there were enough abundance in the source to have them, that would be fine. But in stars, maybe you could imagine a mechanism to get iron swept up into a GRB, but getting uranium would be pretty tough. Yes.
There was sometimes some inconsistency between the way the Harris collaboration fitted their data with the same sort of molecular techniques and shaded. Has this been sort of resolved? Because they were claiming they were seeing protons based on their just Xmax and Auger.
Right. They, to my mind, honestly just did a much, not a very good analysis. They said, we believe the models. And they didn't look at the variation, for example, and they didn't look at the energy dependence. They just picked one energy and said, we're going to believe that QGS Jet 2 properly describes the shower development, and then we conclude it's protons. But to ignore the evidence of the energy dependence, which is not a given, that's not in agreement with any model, and to ignore the variance, and to assume that you know that one model is correct when they're all over the place, just doesn't seem to me to make sense. But that's why there's a discrepancy. It's not a sort of a conceptual disagreement about what's the right thing to do. Yes. I didn't show it, but maybe I can. Oh, nobody noticed this gaucho. He doesn't have an earache. He's talking on the cell phone. No, not. Dick is not smiling at the gaucho. Maybe I can go back and find the time. Basically, a photon-induced shower develops much, much deeper. And were you the person who's just asking? I think so. And so there are no showers simply that are deep enough to be explained by a photon. You can imagine why. It's the electromagnetic interactions are just a lot weaker than.
All right, so there are no more questions. Thanks so much again.
Very nice talk.
Oh, thank
What's
you.
their timing?
My flight's at 4:45.